Okay, hello and welcome to the calorimetry of delta H of reaction, and this is number 2, so make sure you watch the previous video that goes over the notes. This will cover unit 5A, the notes, and sorry about my terrible handwriting, but my normal pen won't connect, so I got backup pen here. And this is going to be 5A notes, and we're going to be going over the problem on page number 13. Okay, so in the previous example, we added a solid into water, and that was how we got the heat exchange. It was basically the process of dissolving. In this case, if we read the problem, we have got a calorimeter, which is basically 2 styrofoam cups. We're going to end up with a lid, but we got to add some things in first here. Okay. So the first thing that we're going to add in is we're going to add 100 milliliters of 0.2 molar CH3COOH, and we know that that is an acid because it says COO, an organic acid. That's basically vinegar. And we're going to add in 60 milliliters of 0.5 molar NaHCO3, which is sodium bicarbonate or baking soda. And once we add the two of these together, so we would have measured their initial, so these are our 2 graduated cylinders. Okay, and we would have added their we would have measured their initial temperatures in their graduated cylinders. And once you've mixed the 2 of those together, the solution had dropped to 21 degrees Celsius. So, okay. So we cannot measure Q for a reaction. That's very, very, very important. We cannot measure that. But we know that Q endo, this is what we start with when we do any calculations, equals negative Q exo. So in this case, we need to define what endo and exo is. So in this case, the temperature of the water is getting colder, which means that the water is actually giving off heat energy, or your solution, so we'll call it solution, okay, which is mostly water, your solvent. And the thing that is absorbing that heat energy is the reaction. And that's why the temperature of the water is going down, because the reaction is basically sucking the energy out of the water. So when we want to do these calculations, we need to do the calculations for the solution. And in order to do that, we need to be able to say, okay, well, Q for solution equals MC delta T. So in terms of mass, we need to get the total mass of all the solution. And this tells us that we have 100 milliliters. I'm not doing the whole MCAT, I'm just finding the mass right now. Plus we have 60 milliliters. And since these are mostly water, we can assume the density is 1. So if we have 160 milliliters, that's going to translate into 160 grams. So that's going to give us our mass. We also are going to be able to use the specific heat. It didn't tell us in this problem, but we're going to assume we're going to be able to use the 4.2, and the units for this is joules per gram degrees C. Okay, that's your specific heat. And then your change in temperature is T final minus T initial. And in this case, our final temperature was 21 because it dropped, minus 27. So our change in temperature is negative 6. And our change in temperature should be negative because we want to get a negative value for the solution, since again, we said that it is exo. So now we can take all of these, and I'm out of room, so I gotta clear some space here so that I can plug all of this in. So we have Q for solution is equal to, and we said that it was 160. And 4.2, or you could use 4.18. And then we have negative 6. And so now we just need to take this, put this into the calculator, and this will give us joules. 6 so Q for the solution is negative, which it should be, 4,000 joules, or negative 4.03, because really we should have two sig figs. I mean, excuse me, three significance. It is three past the two numbers past the decimal, three in total. Okay, so this will give us Q for the solution. We'll then have, all right, so Q for the reaction is going to be positive, and we basically are just going to flip the sign because we know that Q, the negative Q for the solution is the positive Q for the reaction, because where did the reaction get the heat energy from? It got it from the solution, or which is mostly water, basically stole it from the water in the solution. Okay, so we have Q for reaction. How do we turn this into delta H for the reaction? And this is where we need to make it into an, if we remember, intrinsic. We need to make it into an intrinsic property, which means we need to turn this into a proportion. And so we don't want this just to be kilojoules for this specific example. We want to turn it into kilojoules per mole. But in this case, we have moles of two things. And so it's a little harder than the last one, not much harder, but you basically need to figure out which one is your limiting reagent, because that limited how much reaction can take place. So we need to do some limiting reagent calculations, which we're very good at. And there's no equilibrium here, so it makes it really easy. So let's see, we have moles equals, molarity times liters. So for the acid, we have 0.2 times 0.1, because it has to be in liters. So that gives us 0.02. And I'm going to go ahead and solve for carbon dioxide, because it doesn't matter what product you solved for. So I'm going to say 0.02 moles of, let's see, CH3COOH times, there's 1 mole of CO2 for every 1 mole of CH. And it doesn't matter which product you choose. You could have chosen any of them. So this is going to equal 0.02 moles. Okay. Now let's see, we can't figure out a limiting reagent unless we have a competing reaction. All right, so moles is, let's see here. For the baking soda, we have 0.5, and that would be times 60, so 0.6. 0.03. All right, so we have 0.03 moles of HCO3 mole. And we remember with limiting reagents, you always have to solve for the same product. Doesn't matter which product you choose, but whichever one you choose is the one you got to go with. All right, so out of these two, we select the one with this that produces the smallest amount. That gives us our limiting reagent. This value is completely invalid. And 0.02 moles of CO2 tells us how much product we make. We do need to come back over to here, because really this is our limiting reagent. So we don't go with the product, we go with how much the reactant is, right? Because a product can't be your limiting reagent. We use this value to determine that this is the limiting reagent, but that's the value we're going to use. So now we need to take this and turn this into our delta H for the reaction. So we'll remember 0.02. Okay, so we remember that Q for our reaction was positive 4.03, because our reaction was endothermic, and that was our kilojoules value. We divided by 1,000. And we're going to divide this by our limiting reagent, 0.02, and this was moles of our limiting reagent. Okay, so that's not the moles of the product, but the moles of the limiting reagent. And so we get 4.03 divided by 0.02. And we get Q for the reaction is positive 203. Oh, wait, 20. I read that wrong. 202 kilojoules per mole. And this is the value, by the way. You know, when we look up Hess's law and you see the delta H for the reaction next to each one, or when you did equilibrium problems and you saw them over to the right where it would say delta H for the reaction equals, and then it would give you this value. That's how this value is calculated for reactions, is through calorimetry. And that's why this is such a powerful tool to give us values that we can use in other applications. So there will be practice problems. There's a practice lab calculation that I'll post and provide an answer key for. I won't have a video notes for it, but it'll have practice problems in it, and also your review sheet. The last set of video notes that's really important to watch is going to be how intermolecular forces are related to calorimetry. And then also there will be some practice problems on, well, how can I actually use this delta H of a reaction value when I don't have 1 mole? So maybe if I have so many grams, how do I work backwards? How do I actually apply this value to amounts? How do I apply this to stoichiometry? And so there will be some practice problems on that as well. Thank you for listening.